Hello everyone. So let me finish the remaining part of the chemical equilibrium. So listen carefully. Now today I am going to start from relation between degree of dissociation and vapor density. Right. So all of you go through this relation between degree of dissociation. It is represented with alpha and vapor density. Okay, so relation between degree of dissociation and vapor density. So first of all, what is degree of dissociation? It is designated with alpha. Alpha क्या बोलते हैं? Degree of dissociation मतलब क्या? The ratio of number of moles of the number of moles dissociated to the total number of moles. The ratio of number of moles dissociated to the total number of moles is always taken as alpha or degree of dissociation. So write like this: number of moles dissociated by total moles taken initially. Total moles taken initially. Okay. Now, if you consider a gaseous equilibrium, okay, for a gaseous equilibrium, just assume a gaseous equilibrium. So, gaseous state में है, therefore, according to ideal gas equation, for a gaseous equilibrium, according to ideal gas equation, what do you have to take? PV is equal to nRT. Then PV is equal to weight by molecular weight into RT. It can be written as PM is equal to weight by volume into RT. Then PM is equal to dRT, where D is density. So D is equal to kya? PM by RT. Okay, density is equal to PM by RT. Now, so यहाँ तक तो समझ गए होंगे, density is equal to PM by RT. Now, instead of molecular weight, what you can take? Instead of molecular weight, what we can take? Vapor density by 2. So again, take this equation. PM is equal to dRT and M is equal to dRT by P. So instead of vapor density, molecular weight, you can write it as vapor density. So 2 into vapor density, molecular weight means vapor density into 2 is equal to dRT by P. Then vapor density is equal to dRT by 2P. Again, vapor density is equal to dRT by 2. Instead of P, you can write again nRT by P. So RT get cancelled. So finally what you are getting is vapor density is equal to density into volume by 2 into N. So from this, if you keep density and volume are constant, then vapor density is inversely proportional to number of moles. Okay? Vapor density is inversely proportional to number of moles. So first derive like this. So you just derive the relation between vapor density and number of moles. Now we can apply this on an equilibrium. Okay? We can apply this on an equilibrium process. Okay? Right. Now, I am using an equilibrium process like this. So please remember this, vapor density is inversely proportional to number of moles. Okay, N2O4 solid, gaseous N2O4, dinitrogen tetroxide gives rise to 2NO2 gas. Okay. Initially I have taken 1 mole. Initial moles, if you consider initial moles 1, 0. Now it is 2 alpha and it is 1 minus alpha. This is at equilibrium. Okay. Now total moles at equilibrium. Total moles at equilibrium is equal to 1 minus alpha plus 2 alpha. That equal to 1 plus alpha. ठीक? Okay. Now if you consider initial vapor density, that is taken as capital D, is inversely proportional to number of moles taken initially. Okay, number of moles taken initially. Again, vapor density at equilibrium. Vapor density at equilibrium is taken as a small d, and it is also inversely proportional to number of moles at equilibrium. क्योंकि अभी एक डिराइव करके बोले थे ना, vapor density is inversely proportional to number of moles, वही डिराइव करके बोले थे. So इसीलिए vapor density initially लेंगे तो that is inversely proportional to number of moles taken initially, and vapor density at equilibrium is inversely proportional to number of moles at equilibrium. So therefore, capital D by small d is equal to, okay, capital D by small d, इन दोनों का ratio. See, initial moles and moles at equilibrium. So first I will write like this, okay, moles at equilibrium divided by initial moles. Have understand this? So vapor density initially divided by vapor density at equilibrium is equal to moles at equilibrium divided by initial moles. Okay, so for continuation please. So therefore we can write like this. Capital D by small d is equal to 1 plus alpha by 1. Okay. So capital D by small d is equal to 1 plus alpha. Then alpha equal to capital D by small d minus 1. Okay. Alpha is equal to capital D by small d minus 1. And it can be written as finally alpha is equal to capital D minus small d by small d. So this is for the 10 to O4 and MO2 equilibrium के लिए ये ठीक है. ठीक. अगर for a process A n times gives rise to n moles of A. मतलब if the dissociation is like this, then for this kind of n moles of A जो फॉर्म हो रहा है, इसके लिए तब अल्फा कैसे कैलकुलेट करेंगे? सेम फार्मूला, कैपिटल D minus small d by small d into n minus 1. What is n here? N is number of species formed after dissociation. Number of species formed after dissociation. Okay, so this is the formula you have to understand. So you got it. This is the relation between vapor density and as well as degree of dissociation. So आप vapor density जगह molecular weight भी ले सकता है. अगर if you want to take molecular weight, then you have to write the formula like this: capital N minus small n by small m into n minus 1. So instead of vapor density, I have taken molar mass. This is the molar mass of reactant which is taken initially. This is average molar mass at equilibrium. Okay. So capital M minus small m by small m into n minus 1. Like that also you can calculate the degree of dissociation. So please remember, right? Okay. So let me do a question based on this topic, right? इसके ऊपर एक क्वेश्चन करवा रहे हैं, देख लीजिएगा. The question is N2O4 undergoes dissociation in a closed vessel at constant temperature. N2O4 undergoes dissociation in a closed vessel at constant temperature. The vapor density observed at equilibrium, the vapor density observed at equilibrium is the vapor density observed at equilibrium is 30. Therefore, find the degree of dissociation. Therefore, find the degree of dissociation of N2O4. So this is the question. See, N2O4 undergoes dissociation in a closed vessel at constant temperature T. The vapor density observed at equilibrium is 30. Find the degree of dissociation of N2O4. So the equilibrium required here is N2O4 gives rise to 2NO2 gas. So already मैं बोल चुका हूँ आपको एक फॉर्मूला कैपिटल D minus small d by small d into n minus 1. So small n मतलब two chemical species फॉर्म हो गए. तो पहले कैपिटल D, so capital D is equal to molecular weight by 2. Initial vapor density means molecular weight by 2. N2O4 का molecular weight 96 by 96 by 2 कितना है? Wait a minute please. Say N2O4 का molar mass 28 plus 64. Okay, sorry, 92 by 2 that equal to 46. So molecular weight is 92. That's why vapor density is about 46. So alpha equal to 46 minus 30 divided by 30 into 2 minus 1. Again 16 by 30. That equal to 0.533. 0.533. So, or if they ask the percentage, then we can go through 53.3%. 0.533 or 53.3%. Is that clear? So, it's a kind of question, it's important to listen carefully. Okay? So remember this kind of questions you may get in various objective exams, right? Now, let me go to one more and the last topic, Le-Chatelier's principle. Le-Chatelier's and Brown principle. See, Le-Chatelier's and Brown principle. Sir, what is this Le-Chatelier's and Brown principle? What's its use? See, equilibrium. You are studying equilibrium only in reversible reactions, where forward and backward reactions are simultaneously happens. So, if both forward and backward reactions are happens simultaneously, they're never going to end. Process never going to end. Okay, if you constructed an industry and you are using a reversible process, what you want to get is some profit by sale of that product. But you are doing a reversible, so the product yield is very less. Then how you get that profit? You may get loss also. मैं क्या बता रहा हूँ समझ गया? अगर आप एक इंडस्ट्री कंस्ट्रक्ट किए थे, सो जो भी प्रोडक्ट आप वहाँ पे जो भी प्रोडक्ट आ रहा है उसको सेल करके आपको थोड़ा सा प्रॉफिट कमाना है. बट अगर वो प्रोसेस रिवर्सिबल है तो प्रोडक्ट ज़्यादा तो नहीं आएगा. सो प्रॉफिट का जगह लॉस भी हो सकता है। सो यहाँ पे लीचा-क्लियर ब्राउन प्रिंसिपल का यूज क्या होता है ना, तो टू इंक्रीज द यील्ड ऑफ ए रिवर्सिबल प्रोसेस, आर यू गेटिंग इट? टू इंक्रीज द percentage yield of a reversible process, we use this लीचा-क्लियर and Brown principle. Okay, now let me go through the statement regarding this लीचा-क्लियर principle. Listen carefully. When a system of equilibrium, is subjected to, better to say stress, subjected to stress. Sir, what is stress? आप लोग फील करते हैं वो स्ट्रेस नहीं, इनका स्ट्रेस अलग है, ठीक है? So when a system of equilibrium is subjected to stress, within bracket, change in concentration, change in temperature, change in pressure, change in concentration, change in temperature, change in pressure, or addition of inert gas, Okay, when a system of equilibrium is subjected to stress, here stress in the sense change in concentration, change in temperature, change in pressure, or addition of inert gas, then equilibrium is shifted towards the side where the applied stress is nullified, or where the applied stress becomes zero. Are you getting it? So when a system of equilibrium is subjected to stress means कुछ प्रॉपर्टी को आप चेंज कर रहा है, तो तब क्या करेगा? इक्विलिब्रियम आल्सो शिफ्टेड टू काउंटर साइड मतलब when you are increasing concentration in one direction, equilibrium will oppose it, so that it counters the process and it makes the applied change zero. See, for example, I'll explain one by one point wise where you can got it so easily. यहाँ पे कैसे आप हम समझ रहे हैं, तो अगर आप इक्विलिब्रियम के ऊपर कुछ चेंज किए थे, then equilibrium will shift it towards reactant side or towards product side. कहाँ जाने से वो चेंज जीरो हो जाएगा, उस तरफ जा रहा है. So equilibrium is shifted towards the side where the applied stress should be zero. On that side only equilibrium will move. So that is what we call Lichatier's principle. Okay, have understand this? So what you understand now is the position of equilibrium is favored by all these factors. मतलब you can change the position of equilibrium by changing concentration. You can change the position of equilibrium by changing temperature, by changing pressure, or by addition of inert gas. Okay, so equilibrium position. So finally, what you understand? Equilibrium position can be influenced or changed by first change in concentration, second change in temperature, change in pressure, and finally addition of inert gas. Okay, so these points we have to explain one by one. Okay, right. Okay, let me describe one by one. First, effect of change in concentration on equilibrium position. So, effect of change in concentration. Okay. Effect of change in concentration. See, if you consider an equilibrium like this, a reactant gives rise to product. Okay. So please remember a point. If you add reactant to the equilibrium process, already यहाँ पे equilibrium establish हो गया. तो to this equilibrium process we added some reactants. थोड़ा reactant add किए थे. तो अचानक reactant concentration बढ़ गया. तो उसको कम करना है. तो equilibrium कैसे move होगा? Towards product. So forward reaction is favorable. Have understood? When you add reactant to an equilibrium process, equilibrium shifted towards product side to minimize the reactant concentration. Equilibrium shifted towards product side, so forward reaction happens. When you remove reactants, backward reaction. When you add products, again backward reaction. When you remove products, again forward reaction. So like that, if you make some change in concentration one side, equilibrium shifted towards the side by going on which side the effect will be zero. Okay, when you add reactant, then reactant concentration बढ़ गया, उसको कम करना है तो product side जाएगा. So वैसे imagine कीजिएगा, ठीक है? So I am writing point wise. First point, addition of reactants to an equilibrium process. Addition of reactant to an equilibrium process favors the forward reaction. Favors the forward reaction. Okay. Next, removal of reactants favors the backward reaction. Backward reaction. Next, again, addition of products to an equilibrium process. Addition of products to an equilibrium process favors the backward reaction. Right. Removal of products favors the forward reaction. Okay, so like that you should remember. यहाँ पे forward मतलब reactant to product side. Product side जा रहे हैं तो forward. Reactant side आ रहा है तो backward. So like that, in the simplest way you can understand the effect of concentration on equilibrium position. Okay. Now coming to the second one, effect of temperature on equilibrium position. See, effect of temperature on equilibrium position. How temperature influences the equilibrium position? Okay, listen, all of you. Again, if you consider a reactant gives rise to product, it is an equilibrium process. Okay, and here forward reaction is मान के चलिए exothermic. So ऐसा लिखा हूँ, reactant gives rise to product, del H is negative. What does it means? Forward reaction is exothermic. If forward reaction is exothermic, then backward reaction always endothermic. Forward reaction exothermic होगा तो backward reaction क्या होगा? Endothermic होगा. मतलब so when you increase temperature, then equilibrium shifted towards the side where temperature will be consumed. मतलब heat will be absorbed. So increasing temperature favors endothermic reaction. When you decrease in temperature decrease किया, equilibrium process का temperature decrease किया, तो equilibrium किस तरफ जाना पड़ेगा? कहाँ पे टेम्परेचर इंक्रीज होगा उस डायरेक्शन में जाना पड़ेगा, मतलब एक्सोथर्मिक रिएक्शन, बिकॉज वेयर हीट इज लिबरेटेड सो टेम्परेचर विल इंक्रीज. So simplest way you can understand. Don't go for forward backward like this here. So अगर forward exothermic, backward endothermic नहीं है तो forward endothermic है तो backward exothermic. Just go through this exo and endo. According to that you can understand. Okay. So as for this I have taken here it is exothermic reaction. Okay. Backward endothermic ऐसा आएगा. तो मैं ऐसा लिख रहा हूँ conditions. First condition. High temperature favors endothermic reaction. मतलब the reaction should consume heat. That's why endothermic reaction. Okay. And the second point, low temperature favors exothermic reaction. High temperature favors exothermic reaction and low temperature favors endothermic reaction. See, this is the effect of temperature on equilibrium position. Next, effect of pressure. See, effect of pressure on equilibrium position. Effect of pressure. Okay. See, if delta N of the process is 0, no effect of pressure. Understand? If delta N is equal to 0, then there is no effect of pressure. Okay. Sir, ऐसा क्यों sir? Why sir? See, already we explained about degree of dissociation in previous class, right? So let me go through that point again. Just to take like this, H2 plus I2 gives rise to 2 Hi. 1 mole, 0 mole. 2 alpha, 1 minus alpha, 1 minus alpha. These are the number of moles. So total moles at equilibrium. Total moles at equilibrium. This is equilibrium position. This is initial position. Total moles at equilibrium 1 minus alpha plus 1 minus alpha plus 2 alpha. So how much you are getting? 1 minus alpha, 1 minus alpha plus 2 alpha. So you are getting 2 moles. Okay. Then partial pressure of Hi. So 2 alpha by 2 into total pressure. Partial pressure of I2 1 minus alpha by 2 into P. Partial pressure of H2 also same 1 minus alpha by 2 into P. Okay. Then what is the expression to calculate Kp? So Kp is equal to partial pressure square of Hi by partial pressure of H2 into partial pressure of I2. So 4 alpha square, right? So 2 alpha by 2 ये कैंसिल हो जाएगा, कैंसिल कर लेते हैं यहाँ पे. तो यहाँ alpha square into p square by 1 minus alpha by 2 into p, 1 minus alpha by 2 into p. So p square p get cancelled. तो यहाँ पे क्या मिला आपको? So 4 alpha square by 1 minus alpha into 1 minus alpha. So 1 minus alpha whole square. So this is Kp. But in this expression there is no pressure term. In this expression there is no pressure term. Okay. So I think it's may not visible. I think. Listen. I'll write this one at the top. Okay. So up to this much it is visible, but the Kp is not visible. I think. So the Kp is equal to what we are getting? 4 alpha square into 1 minus alpha whole square. So in this expression there is no pressure term. There is no pressure term in the numerator or in the denominator. Wherever it may be, there is no pressure term. That's why it is not affected by pressure. समझ गया? So that's why if delta n of the process is 0, there is no effect of pressure. Okay. अगर delta n पॉजिटिव और नेगेटिव होने से तब इफेक्ट ऑफ प्रेशर रहेगा. समझ गए? Okay. So that also can be explained in the similar way, right? But we can go for shortest way here. For exam purpose of you, let me go through in shortest way. Okay, guys. If del n is not equal to 0, if del n is not equal to 0, next. In such process, equilibrium position changes with change in pressure, right? If delta n is not equal to 0, in such process equilibrium position changes with change in pressure. Equilibrium position changes with change in pressure. ऐसे इसमें shortest way कैसे हम explain कर सकते हैं? See, as the pressure increases on equilibrium system. We used to take always a gaseous equilibrium system. As the pressure increases on the equilibrium, gaseous equilibrium system. अरे as pressure increases, volume क्या होगा? Decrease होगा. तो equilibrium shifted towards the side where number of moles are less. And when you increase pressure, the equilibrium shifted towards the side where volume is less or number of moles are less. So that is the shortest way you should remember. As pressure increases on gaseous equilibrium system, then equilibrium is shifted towards the side where number of moles are less. Okay. Next, अगर इसका counter change, as the pressure decreases, on the gaseous equilibrium, then what happened? Then equilibrium is shifted towards the side where number of moles are more. Okay. So, like that you should understand effect of pressure on equilibrium position. Now coming to addition of inert gas on equilibrium position. Okay. Okay, now if you go to addition of inert gas. See, if inert gas is added, to an equilibrium position, at constant volume, if inert gas is added to an equilibrium position at constant volume, there is no effect. ऐसा कुछ change तो नहीं होता. If inert gas is added to an equilibrium position at constant volume, there is no effect. अरे volume is already constant. If volume is constant, the concentration remains constant. No change in the concentration. Okay, अगर if there is no change in the concentration, equilibrium position की इस तरफ move होने का जरूरत ही नहीं है, और equilibrium constant also remains same. Okay, so have understand if inert gas is added at constant volume, there is no change in the equilibrium position. It remains as it is. Because if you keep volume constant, then concentration remains the same. Number of moles per unit volume remains constant. Then there is no change in this one. If you go according to the partial pressure way, see, if you added inert gas at constant volume, the partial pressure may becomes partial pressure may changes. Okay, partial pressure may changes, but यहाँ पे inert gas का भी partial pressure आ जाता है ना, right? So if inert gas is added to an equilibrium position at constant volume, there is no effect, right? Next, if second point, if inert gas is added to equilibrium position, if inert gas is added to an equilibrium position at constant pressure, okay, if inert gas is added to equilibrium position at constant pressure, if delta M is equal to 0, no effect. See the same way, Kp or Kc expression, अगर Kc expression लेंगे तो there is no volume term ऊपर और नीचे, मतलब न्यूमरेटर और डिनोमिनेटर में वॉल्यूम टर्म नहीं रहता. Kp terms में भी if you take Kp also, there is no volume or pressure term in numerator or denominator. That's why if delta M is 0, there is no effect. Okay. Next, if delta M is not equal to 0, there will be there is an effect. Okay, there is an effect. So how? See, by adding inert gas at constant pressure, equilibrium shifted towards the side, where number of moles are more. See, by adding inert gas with constant pressure, equilibrium shifted towards the side where number of moles are more. See, towards dissociation side it will move. Okay, to increase the alpha value, it will move towards the number of moles are more. So that's it. It's about effect of addition of inert gas. Okay. See, in simplest way I'm telling, as an exam point of view, you just go through like this. So addition of inert gas, if you see, if inert gas is added to the equilibrium position at constant volume, there is no effect of there is no effect of inert gas at all on the equilibrium. If you added it to constant pressure, it may हो सकता है. अगर उसमें भी conditions है, del n is equal to 0, no effect. If del n is not equal to 0, then there will be an effect. So what kind of effect you notice? As we add inert gas, then equilibrium shifted towards the side where number of moles are more. That's it. Understand? So that chemical equilibrium part is completed. Okay. So in next class, I try with a new chapter and a new concept like that. Okay. So I love you. Bye bye. Please like, share, and subscribe my videos. Thank you.